Okay, so it's 7:05 now, so let's start. So hi all, welcome to today's fun math workshop. We'll be talking about base conversions today. And so we'll first go over what number bases are. And so don't worry if you don't know anything about them. And afterwards, we'll see various types of base conversions and how to utilize them. And at the end of the session, we'll end with two very interesting exercises. So let's get started with the base conversions. So first of all, many of you probably have heard of terms like binary, ternary, octal, decimal, hexadecimal, and so on and so forth. And so we'll first look at the term decimal. So a decimal number system is the number system that we typically use. And so we'll have numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, and on, using Arabic numerals. And we see that we use 10 digits. And those are our digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we use these digits for all the whole numbers we write. But in fact, there are more possible ways to write a number system. And a number base illustrates this idea. So firstly, a number base is a system that we can use to count. In a number base, each number can be written as a combination of digits. So when we deal with number bases, we first need a base and then also a set of digits. When writing a number in another base, we typically write it as the number followed by a subscript b. And this subscript b is the base that we want. And also, not every number can be a base. Formally, only whole numbers greater than 1 can be the base of a base system. So, for example, we typically won't have our base being something like 1.5, or we won't have our base system being with base 1 or 0. So the base of our base system can be 2, 3, 4, and so on. It cannot be 1, it cannot be 0, and it cannot be a fraction or an irrational number. So not every number can be a base. So as an example, let's look at base 2. In base 2, there are two digits, which are 0 and 1. So this is base 2. And we will denote these digits in our Arabic numerals, which are 0 and 1. And in this base system, we can write all numbers as a combination of zeros and ones. So for example, if we wanted to write 1, we would just write 1. If we wanted to write 2, we would have 1, 0. And next we'll have 1, 1. And then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, and so on. So this is the number in base 2 for 1. This is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, and we can have more and more numbers. So in binary, there are only zeros and ones, and no other digits are allowed. And okay, so binary is what we call base 2. Somebody asked a really good question. Are there decimals and negatives in bases? Yes, you can have decimals and negatives in bases. It's typically like a bit more complicated. So we know that we have decimals and negative numbers in decimal. So for example, we could have the number 1.09 in decimal. And similarly, we can have decimals in base 2. So for example, we can have this number. And we can also have this number. So these are both in base 2. This number will be 1.1011 repeating. So when we write this, it'll be like 1.1011, 1011, 1011, and so on. And we can also have negative numbers. So for example, in decimal, we have the number -2. In base 2, or binary, we can write -2 as -10, sorry, -10 in base 2. So yeah, this is base 2. And also there are base 3, base 4, and so on. In base 3, or ternary, the only digits are 0, 1, and 2. And all numbers are expressed as a combination of zeros, ones, and twos. So for example, in ternary, we could have a number like 1, 2, 3. Sorry, there's no 3. 120.021, and we could have the 1 repeating. So this is a valid ternary number. So this is base 2, this is base 3. And we have all these names for base systems. Decimal is just base 10. And yeah, so this is a number that can be expressed in base 3. And we can actually convert this to base 10. So for most of today, we'll focus on whole numbers because they're more elementary and they won't include too many advanced ideas. So yeah. And also there are base 3, base 4, and so on. So here we have base 2, base 3. This octal is base 8. And in base 8, or octal, the only digits are 0, 1, 2, 3, 4, 5, 6, and 7. And all the numbers can be expressed in this way. So in particular, in base 8, we cannot have the digit 8, and we cannot have the digit 9, because in base 8, there are only 8 digits, which are 0 through 7. And similarly, there's no digit 2 in binary, there's no digit 3 in ternary, there's no digit 10 in decimal, and so on and so forth. But now let's look at the case where there aren't enough digits. So now let's look at base 16, or hexadecimal. So here we're answering the question, what if there aren't enough digits to write the number? So in base 16, we need 15 digits, one for each of 0, 1, 2, 3, and so on until 15. But in Arabic numerals, we only have digits for 0 through 9. So we don't have enough digits. We still need a digit for 10, 11, 12, 13, 14, and 15. So we create 6 new digits for 10, 11, 12, 13, 14, 15. And these 6 digits will be called A, B, C, D, E, and F, respectively. So in hexadecimal, the digit for 10 will be A, the digit for 11 is B, the digit for 12 is C, the digit for 13 is D, the digit for 14 is E, and the digit for 15 is F. And so, for example, we could have a number like 1EF in base 16, or we could also have a number like 1D point DC1 repeating. And in base 16, we also have the digits 0 through 9. So we could also have a number like this. And so these are just some base systems that we typically see. So like we have binary, ternary, octal, decimal, hexadecimal. And some of them are often seen in things like computer science. And so yeah, here's the introduction to base systems. So do any of you have any questions so far? I'll wait a minute or so for you guys to digest this information, and then we can move on to the next topic. So if you have any questions, feel free to post them in the chat. All right, so I haven't gotten any questions, so we can move on. And so next we'll look at how we count in some of these base systems. So in base 2, so this is binary, we start with 1 for 1, and then 1 0 for 2, 1 1 for 3, 1 0 0 for 4. So we'll have 1 2 3 4, and we kind of just count in this way. So we add 1 to the units digit, and if that fills up the units digit, we add it to the 2's digit. And then when the 2's digit is full, we add the digit to the 4's digit, and so on. So for example, 12 in base 2 is equal to 8 plus 4. And 8 is equal to 2 cubed, and 4 is equal to 2 squared. And in base 10, we have the number 1100 is equal to 10 cubed plus 10 squared. So you see the similarity in these two expressions. And so for 12, the way we write 12 in binary is 1100, because we have 2 cubed and 2 squared. So this is how we count in binary. And we can count similarly in ternary. So we'll start with 1, 2, and for 3 we'll have 1 0. For 4 we'll have 1 1. For 5 we'll have 1 2. For 6 we'll have 2 0. For 7 we'll have 2 1, and so on. And when we get to 9, so this is 9. When we get to 9, we'll have 1 0 0, because 9 is 3 squared. And then we can keep counting. 10, 11, 12, 13, 14, 15. And similarly, we can count in octal, which is base 8. We'll start with 1, 2, 3, 4, 5, 6, 7, and then we'll go up to 1 0, which is 8, 1 1, which is 9, and so on. And similarly with hexadecimal or base 16, we'll start with 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F for 10 through 15, and 1 0 for 16, 1 1 for 17, and so on. And you notice that after 1 9, which is 25, we have these 6 numbers: 1A, 1B, 1C, 1D, 1E, 1F. And if you go far enough, you'll also find numbers like DE, AB, or numbers that could be entirely expressed with digits from 10 to 15. So such numbers exist. And so this is how we count in base systems like these. And also as a fun fact, in ancient Mesopotamia, in the Sumerian and Babylonian cultures, base 60 was used. And also in some cultures in Papua New Guinea, they used base 6 or base 15. So in fact, there are places in the world that do not or have not primarily used base 10. All right, so I'll wait for any questions about counting in base systems. And after a minute or so, if I don't receive any questions, we'll move on to base conversions. All right, so let's move on to our next topic, which is converting in bases. So first, we'll talk about the base B system. So we have our base B representation of a number. So like we have xn, xn minus 1, xn minus 2, and so on until x1, x0 in base B. And so such a number, we can convert it to base 10 by using this formula or this definition. So this is how we define a base B representation. We see in this definition, this number can be written as this. So we'll have xn times b to the n plus xn minus 1 times b to the n minus 1, and so on until x0 times b to the 0. So for example, the number 102 in base 3 is equal to, when we can use the definition for converting, this would be equal to 1 times 3 squared plus 0 times 3 to the first power plus 2 times 3 to the 0th power. And this is equal to 9 plus 0 plus 2, which is equal to 11. So converting from base B to decimal is quite straightforward because we could directly use this definition and calculate. And so as another example, if we have a number like A1.6, and this is in base 11, we can write this as 10 times 11 to the first power plus 6 times 11 to the 0th power, and plus, sorry, this should be 1, and plus 6 times 11 to the negative first power. Similar to what we have in base 10, since when we have digits after the decimal point, we basically have multiplying by 10 to the negative power. And here we have the same thing. We have 6 times 11 to the negative first power. So this will give us a result of 111 and 6 over 11. You can also write this as 1227 over 11. And so this is how we convert from base B to base 10. And it's also the definition of a base B representation. And so we'll look at a bit more examples. So I'll give you guys 3 minutes to try converting these numbers to decimal. And oh, I can go back a slide, sure. This definition is just for whole numbers. If you want a definition for all real numbers, we can write this. So we'll have a decimal digit. We have a decimal point here, and x -1, x -2, x -3, and so on. This in base B is equal to this thing. But we'll continue on the negative side. So plus x -1 times b to the -1 plus x -2 times b to the -2, and so on. That's a -2. All right, so now I'll give you guys around 3 minutes to try these examples by yourself. All right, so 3 minutes are up. So you guys can keep working, but I'll start to present these conversions. So for our first example, we have 3215 in base 7, and we want to convert this to base 10. So we use our definition, which is up here. So we'll have 3 times 7 cubed plus 2 times 7 squared plus 1 times 7 plus 5. And this is equal to 3 times 343 plus 2 times 49 plus 7 plus 5. And we can calculate each of these. This is 1029, this is 98, and these are 7 and 5. And we can add these up for and we'll get 1139 as a result. So this is our first example. And for our second example, we have A91 in base 11. And we want to convert this to base 10. So the digit 8 is the same as 10. So like in decimal. And so we'll have 10 times 11 squared plus 9 times 11 plus 1, which is equal to 1210 plus 99 plus 1, which is 1310. So that's our second example. And for our third example, so we want to convert AE in from base 15 to base 10. So the digit A represents 10, and the digit E represents 14. So when we multiply this and add, we get 164. So are there any questions about any of these conversions? All right, so since there are no questions, I'll move to the next topic, which is converting from decimal to base B. So when we convert from decimal to base B, we're basically doing the opposite process. So if we want to take this number and we want to, if we want to take a number and we want to express it in base B, we'll have to use, or a nice trick is using this. So what is this? So I'll introduce this idea with an example. So I'll do this first example here. So I want to convert 341 from decimal to base 7. And so how we do this is we want to find each digit one by one. And so what we do is we write this thing equals B times the first n minus 1 digits and then plus the last digit. So really what's happening here is we're doing division by B. So we'll take 341 and we'll divide it by 7. So you can do your division and you'll get 48 with a remainder of 6 or 5. So you'll get a remainder of 5, and that will be our unit digit in our base 7 representation. And next, we take 48 and we divide by 7 again. So 48 is our quotient, and we want to divide it by 7 again to get the last digit in the first n minus 1 digits. So we'll have a quotient of 6 and a remainder of 6. And so our second remainder is 6. So this will be the 7th digit. And lastly, we see that we have a 6 on the as the quotient, and 6 is less than 7. So we directly put this as our first digit. So we'll end up with the number 665 in base 7. And we can quickly confirm this because we can notice that 341 is equal to 343 minus 2, which is equal to 1000 in base 7 minus 2 in base 7. And when you subtract, you can quickly see that this is equal to that. So that's our first conversion. And so I'll give you guys the second one as an exercise now. So you guys can have a minute or so to work on the second one, and then I'll present the solution. All right, so I think I'm having a bit of internet issues. So you guys can work on the third example if you have the time. All right, great. My internet is back. So we can continue on our next example. So we want to convert 1524 or 1524 to base 5. And so we'll use the same idea. So what we'll do is we'll divide 1524 by 5, and we'll take the remainder. So we'll have 304 as our quotient and 4 as our remainder. So 4 will be our last digit. And we do the same with 304. We divide it by 5, and we're going to get 60 as our quotient and 4 as our remainder. And for 60, we divide by 5 again, and we'll have 12 as our quotient, 0 as our remainder. We do the same with 12, quotient 2, remainder 2. And we're left with 2 for our first digit. So good job if you got this as your answer. And if you want to know the answer for the last one, it is 60306 in base 12. So yeah. All right, next topic is converting from binary to octal. So when we're converting from like binary to base 4 or base 4 to base 16, there are a few tricks that we can use. So since 8 is a power of 2, we can group powers we can group some digits together. So for example, when we want to convert from binary to octal, we can consider groups of 3 digits. So we'll start from the end of the number, and we'll take groups of 3 digits, and we will convert each of these. So for example, if we want to convert this number, we will convert each of these groups of 3 digits to base 8. So in our last group of 3 digits, we have 001, which is 1 in base 8. Our second to last group of 3 digits is 011, and 011 is 3 in base 8. And 100 is 4, so we'll have 4. And then 10 is 2. So we're going to end up with the number 2431 in base 8. And to convert from octal to binary, or base 8 to base 2, we do the same thing but reversed. So we'll take 1 and we'll replace it with 001. We'll take 3 and we'll replace it with 011. And we'll take 4 and replace it with 100. And 2 and replace it with 10. And so, in fact, what we have just done is this example right here. And as another example, we can do this one. We'll take groups of 3 digits and we'll convert each group to base 8. 100 is 4, 000 is 0, and just a 1 is also just a 1. So this is our second example. All right, so these are some, this is a way to convert from binary to octal. All right, so what if you wanted to convert, say, from base 4 to octal, or base 4 to base 8? So let's look at an example. So let's say we wanted to convert 1332 in base 4 to base 8. How would we do this? Does anyone have any ideas? All right, somebody replied with a really good idea. So what what this person wants to do is maybe we first can convert to base 2, since converting from base 4 to base 2 is easy, and converting from base 2 back to base 8 is also easy. So rather than converting to base 10 and then to base 8, which is more complicated, we can first convert to base 2 and then convert to base 8. So this is a great idea. To convert this number to base 2, we do something similar to converting base 8 to base 2. We take these digits and we represent them in base 2. So 2 will become 1, 0, 3 will become 1, 1, 3 will become 1, 1, and 1 becomes just 1. And this will be our base 2 representation. And one thing to be careful of is that when we do something like this, one base has to be a power of the other. So we can do this with 3 and 9, but we cannot do this with 4 and 6. So now that we have converted this base 4 number to base 2, we can convert back to base 8. So to convert this number to base 8, we take groups of 3 digits like this, and we write them in base 8. So 110 denotes 6 because 110 is 4 plus 2, which is 6. 111 denotes 7 because 111 is 4 plus 2 plus 1, which is 7. And our last one becomes a 1. So now we have successfully converted this number 1332 from base 4 to base 8, in which it is 176. So this is a nice little trick that you can use to convert bases that are powers of the same number. Any questions? So on our next 2 slides, we have converting from octal to binary, which we just talked about as well, and converting from nonary, which is base 9, to ternary, which is base 3. And this is the same idea as well. So let's see what it looks like with this example. So here, what we do is we convert each digit from base 9 to base 3. So for 8, it becomes 2, 2. For 1, we have 0, 1. For 7, we have 2, 1. For 3, we have 1, 0. And for 1, we just have 1. So what we did here was we converted each digit from base 9 to base 3. So are there any questions about this? It's mainly the same idea as converting from base 8 to base 2 or base 4 to base 2. And we can do the same thing but backwards to convert from base 3 to base 9. So I'll wait a minute or so to get any questions. Will you do any questions today? Yeah, we'll look at 2 interesting questions after we go over the conversions. So next we'll look at some more conversions. Now we're doing the most general case where we want to convert from this base to that base, and the two bases have almost nothing in common. So for example, we want to convert from base 19 to base 13. And since 19 and 13 are not powers of a common prime or powers of a common number, we can't use any of the tricks that we just talked about, which we used for converting base 8 to base 4, or base 8 to base 2, or base 3 to base 9. So here, what we want to do is we want to first convert from base 19 to base 10, and then converting from, and then we want to convert from base 10 to base 13. So the reason we want to first convert to base 10 is because it's easier to convert from base 10 to base 13 than directly convert from base 19 to base 13, because we don't typically use base 19 or base 13. So base 10 is kind of like a point of reference in this conversion. So let's look at our first example. We want to convert 1 to G, where G is the digit for 16 in base 19. We want to convert this to base 13. And so first, we want to convert to base 10. So what is this number in base 10? Well, we can use our definition. So we'll have 1 times 19 squared plus 2 times 19 to the first power plus G, which is 16. And what we'll get from adding these is 136. Sorry, not 136. This is 361 plus 38 plus 16, which is equal to 415. And so now we've converted from base 19 to base 10. And so next thing we're going to do is we're going to convert from base 10 to base 13. So base 13. And to do this, we do what we usually do. We divide 415 by 13 and take the remainder. So when we divide, we'll have 32, I believe. And our remainder will be 3. So our last digit will be 3. So let's write this. 415 in base 10, and in base 13, our last digit will be 3. And so what we're left with is 32, which is our quotient. And we divide this by 13 again, and our quotient is 2, and our remainder is 6. So our first digits are 2, 6. So this is our final base 13 representation of this number. So are there any questions about this? Feel free to ask. And also, this is not 32, so my bad. This should be 31, remainder 12. In fact, this is not 263. So our remainder is 12. So our last digit will be actually C, because the digit for 12 in base 13 is C. And we can also take our quotient and divide by 13. So we'll repeat this process, and we'll have quotient 2 and remainder 5. And so our first two digits are actually 2 and 5. So it's always a nice sanity check to check if your number, your conversion actually works by converting back. So you can quickly see that the number I had, which is 263, is not equal to 415 in base 10 because 263 base 13, when we convert this to base 10, we actually get 419. So this is always a good sanity check to convert back to see if you actually got the right numbers. So this will be our final base 13 number. All right. So are there any questions about converting kind of like random bases to random bases? I included 2 more examples here in case you wanted to try them. But we'll skip these for now. Sorry about that. We'll skip these for now. We'll skip these 2 examples for now. While I wait for my internet to respond again. And now you guys can think about these 2 examples. So, sorry, these 2 exercises, which are our 2 questions for today. And if you have any ideas, feel free to type them in the chat or send them to me. And after a few minutes, we'll talk about the solutions to these 2 exercises. All right, so now uh, we can start. All right, so now we can start to go over these two exercises. So can you all see what I'm screen sharing? All right, I'm getting a few yeses, so we can start talking about these two exercises. So we have a polynomial with only non-negative integer coefficients. And we're given two values of this polynomial. So at x equals 1 and x equals 17. And so when x equals 1, the value of p of x is equal to 24. And at x equals 17, the value of p of x is equal to 1000. And we're asked, what is the value of p of 2? And so one thing you can notice is that the representation for a polynomial is very similar to the representation for base b or base 17. So one idea you may have is to convert 1000 to base 17. So you can do the division that we usually do. So we divide 1000 by 17, and we'll be left with 5, 0, 0, not 5, 0. So we'll have actually 58. And the remainder will be 14. So our last digit, our units digit will be 14. And 14 is E. And then we can take our quotient 58 and divide this by 17, and we'll get quotient 3 and remainder 7. And so our 17th digit will be 7. And then our 17 squared digit will be 3. So our base 17 representation is going to be 3, 7E. And I'll erase this for now. This can also be written as 3 times 17 squared plus 7 times 17 to the first power plus 14. And so when we look at these coefficients of 17 squared, 17 to the first power, and our unit digit, you notice that these three sum up to 24. And so if our polynomial is p of x is equal to 3x squared plus 7x plus 14, these two conditions are satisfied because 3 times 17 squared plus 7 times 17 plus 14 is equal to 1000. And 3 times 1 squared plus 7 times 1 plus 14 is equal to 24. And because of the nature of base 17 representation, this is actually going to be the only way we're going to have such a polynomial to satisfy these two conditions. Because the other ways to express 1000 as the sum of 17 squared times something plus 17 to the first power times something and a constant is going to be having larger coefficients because of the nature of carrying and having base systems. So this is actually going to be the only polynomial p of x that works. And once we have this, we can directly calculate p of 2 is equal to 40. So 40 is our answer. And now let's look at our second exercise. We want to convert 7/3 to hexadecimal. So one thing you could do is you could do using the dividing by 16 and taking the remainder, but it's going to be kind of complicated. So more interesting way is to separate 7/3 as 2 plus 1/3. So this is equal to actually 2 plus 1 minus 1, sorry, this is equal to 2 plus 1/4 over 1 minus 1/4. And what we're doing here is we're writing 1/3 as a geometric series of 1/4. So in fact, we can write this as 2 plus 1/4 to the first power plus 1/4 to the second power, and so on, infinitely. So this is interesting because now we have these numbers. And so since we already have these numbers, we can start to convert to hexadecimal. So we can pair up adjacent terms in this infinite series. And we can take 2 plus, this is going to be 4/16 plus 1/16. So this gives us 5/16. And after this, we'll have 5/16 squared for the sum of our next two terms, which are 1/4 to the third power and 1/4 to the fourth power. And then we'll have 5/16 cubed, and so on. So in fact, our hexadecimal representation of 7/3 will be 2.5 repeating in base 16. So I'll wait for any questions about this, and then that'll be it for today. All right, so that's it for today. Thank you all for attending our LogiStem Fun Math workshop. And if you wish to attend more of these workshops, you can also check on our website. So that is logistem.club. And the next Fun Math workshop will be hosted by Jesse, who will talk about the law of cosines and law of sines. It'll be on October 17th, which is next Sunday, and it'll start at the same time. So I hope you all learned something new today, and thank you all for attending, and we hope to see you in our next Fun Math workshop. Thank you all.